Welcome to this talk about sensor location optimization for effective and robust beamforming. Here's the outline. So first is introduction to beamforming, including narrowband beamforming and wideband beamforming. And then we talk about the design of narrowband sparse arrays, followed by the design of wideband sparse arrays. And then finally, its conclusion. First is introduction to beamforming. So the aim of beamforming is to effectively estimate the signal of interest, so SOI, in the presence of noise and interferences with the aid of an array of sensors at different spatial locations according to a given geometry. So this is for the receiving mode. Beamforming can also be achieved for the transmission mode. And we have all kinds of arrays based on different criteria. For example, based on the bandwidth of the signal, we can have narrowband arrays and wideband arrays. So we have narrowband beamforming and wideband beamforming. And based on the spatial layout of the sensors, we have linear arrays, planar arrays, and volumetric arrays. So like one-dimensional arrays, two-dimensional arrays, and three-dimensional arrays. Based on their spacing, we have these uniform arrays. So basically the spacing is fixed between adjacent sensors. It's uniform arrays. And also we have non-uniform arrays, or we can also call them sparse arrays. For sensor location optimization, after the optimization, the spacings between different sensors, between adjacent sensors, any set of them or pair of them is not uniform anymore. So that's why, in this talk, although the title is sensor location optimization, but here in section 2 and 3, we talk about the design of sparse arrays, right? Sparse arrays is another way. So design of sparse arrays is another way of saying sensor location optimization. And then based on the construction of individual sensors, we have the traditional scalar sensor arrays. They are the most widely studied ones. And also we have vector sensor arrays. For example, we have cross-dipole arrays, triple arrays, and also acoustic vector sensor arrays. Now for beamforming, for the narrowband case, so narrowband beamforming is achieved by changing the phase and amplitude of the received array signals. So you see this structure, this figure. So we used a linear array as an example. So in total, we have big M sensors, and each sensor you have a received signals. You have X0T, X1T, and so on. And for this narrowband beamformer, each received signal, like this X0T, is multiplied by coefficient W0. Is complex valued, so it's changing the phase and amplitude of this X0T. So you have this W0, W1, and so on. So this beamformer output YT is an instantaneous linear combination of the received sensor signals. So instantaneous linear combination, that means, okay, there's no time delay involved. So it's different from the wideband case. In this figure, you also have this tau 1, tau 2, and so on. So this tau m, so it's given by dm sin theta over c. C is the propagation speed, and theta is the angle of arrival of the signal measured from the broadside of the array. And dm is the distance from sensor 0 to sensor m. That's tau m. So that's the beamformer structure for the narrowband case. And based on this, you can derive the beamformer response or beam pattern of this narrowband beamformer, okay, given by P omega theta. For the narrowband case, so omega is fixed. And this is the standard result. So W is a coefficient vector, Hermitian transpose times this A omega theta. This A omega theta is the steering vector of the array given by this coefficient. And this W you see is including all the beamformer coefficients, W0, W1, and so on. And however, you have this extra operation is conjugate operation, but you also have this conjugate Hermitian transpose, and here's conjugate. So these two conjugates then cancel each other. That's a standard formulation and standard way to formulate this W. And for a particular beamforming task, you can find, so given this P omega theta, suppose you know this, that's the one you want to design, and you find the W, which gives you the desired response, right? So how do you find this W? If you change the frequency omega, you see this W will change, right? So given this, you want to find the best W, and if you change the frequency, then surely this W will change too, right? That means for the wideband case, because each wideband signal consists of an infinite number of different frequency components, right? Then this optimum W here should also be frequency dependent. So you have this W for the wideband, for narrowband case, okay, it's independent of omega because omega is fixed, and you can ignore the omega part. However, for wideband case, this W should be a function of omega. And in digital signal processing, we studied, okay, we know that to have a frequency dependent response, you can have a FR filter or IR filter, so finite impulse response filter or infinite impulse response filter. As a result, so in this narrowband structure, this W0 will be replaced by a frequency dependent response that is so replaced by this FR or FIR or IR filter. So you have this new wideband beamforming structure. So you have X0n, so you sample the signal in the discrete form. So X0n, X1n, and so on. You this is the delay, so it's basically a sampling period. So each delay, you have this coefficient, so W00, W1, and so on. You have in total big J of them. So we call this is a FR filter. And for the continuous case, so here you have X0t, X1t, and so on. Then you have YT here. So the signal flow through these circuits, continuously. In that case, we call it type delay line. So that's a delay between types, adjacent types. That's the analog case. We call it the type delay line. For the discrete case, we call it FR or IR filters. Okay, that's the wideband beamforming structure. So compared to the narrowband case, when J equal to 1, so you only have this left. It's reduced to the narrowband structure. So narrowband structure is a special case of this wideband structure. And then there's another way. So this FR filter or type delay lines, IR filters, is just one way to achieve this frequency dependent response W omega. There's another way. So we call it sensor delay lines. Basically, you put more sensors behind the original sensors, behind the original array sensors. In this case, if you have an original linear array, this X11, X21, X big M1, and so on. This is the original sensor. You put more sensors behind them. If the original array is a linear array, then put more sensors behind this linear array. You have a planar array in this case. You see this structure. So you have, compared to this, you replace this type delay by what? By propagation delay, signal propagation delay here. So these two structures, this part is performing a frequency dependent response. It's trying to, you can design the coefficients to achieve this frequency dependent response here. But there's difference between this structure and this structure, right? Because this structure, the delay is fixed. No matter which direction the signal comes from, you have a fixed delay between adjacent types. But for this sensor delay line structure, the delay between these adjacent types is dependent on the direction of the signal. So they have different performance, but the idea is the same. So we are trying to achieve a frequency-dependent response, W omega. So that's the wideband beamforming structure. Then one question to ask is, okay, when do we need this narrowband structure? When do we need this wideband structure? Okay, in general, if there's some degree of the correlation effect between signals received at the first and the last sensors of the array, then it would be beneficial by employing the wideband beamforming structure. If the signals received by the array sensors, they are coherent, then you don't need to employ this wideband beamforming structure. The narrowband one will work very well. And in this talk, we'll focus on the structure with TDLs, so type delay lines, or FR, IR filters. However, the solutions introduced here can be easily extended to the SDL case. And then for this wideband beamforming structure with TDLs, so we use YT, so XT, right? You delay this XT by integer multiples of this unit delay TS, okay? And then you multiply these delayed versions of the received signals by these corresponding coefficients, beamformer coefficients, and you add them together, you got this beamformer output. And you put them into a vector form. So all the vectors of the, so you put all the coefficients of the beamformer into a big vector. So it's W0, W1, WG minus 1. So for each J, you form a vector. So, okay, you see here for each this slice of this these coefficients, W00, W10, W20, and so on. For this, you form the vector W0. For this, you form the vector W1, and so on. So then you put all the W0, W1, W2, and so on into a bigger vector. So you have this W, and you also put the conjugate here so that you have this W is Hermitian transpose, okay? And then times this xt. Xt is the received signal vector. You arrange the signals in the same way as this beamformer coefficients. So you have x0t, x1t, minus ts, and so in total you have j, big J of them. And for each vector, like this x0t is given by, so x0t is given by the signal at this set of points. And then x1t is a signal at this set of points. So you have this standard form. And then you can see that with this formulation, it's general. So this notation incorporates the narrowband beamformer with the special case of J equal to 1. And similarly, you can derive the beamformer response for the wideband case. So given by W Hermitian transpose times A. A is the new steam vector. W is defined already. A is the new steam vector. The first big M elements is the same for the narrowband case, but you need to add this. For the wideband case, you need to add these extra delays, so TS, and then 1 TS, 2 TS, until J, big J minus 1 times TS. So you have this big steering vector for the wideband case. Now, we talk about the design of narrowband sparse arrays. So first question is, why do we need this sparse array, right? So uniform linear arrays have been widely employed, and they are working well, right? But why do we need these sparse arrays then? So the reasons, okay, because of these benefits, okay. So sparse arrays, they have non-uniform spacings by definition. They allow mean adjacent separation between adjacent sensors, right, to be larger than lambda over 2. Because for uniform linear arrays, to avoid spatial aliasing, you have to make sure the adjacent spacing is smaller than or equal to lambda over 2. But for the sparse arrays, this average separation, this spacing could be larger than lambda over 2. And this leads to a larger aperture size for a given number of sensors. Then you have a higher resolution because you have a larger aperture size. Also, so less number of sensors implies a saving in cost, weight, etc. So given a fixed aperture, the number of sensors will be reduced. Then you have savings in cost, weight, and so on. And this is for the, so here in this talk, we focus on beamforming. Actually, sparse arrays, they play a very important role for DO estimation, for underdetermined DO estimation. So underdetermined DO estimation means, okay, you have the number of source signals is much more than the number of physical sensors. And in that case, how do you perform direction rival estimation? So sparse arrays can provide much more degrees of freedom for DO estimation so that you can achieve underdetermined DO estimation. So they are very important for the DO estimation side. Now, sensor location to design these sparse arrays, right? So we need to do this sensor location optimization. And sensor location optimization is traditionally formulated as a non-convex problem, and is solved by genetic algorithms similar to annealing, like particle swarm optimization, all these similar algorithms with all kinds of fancy names. However, so these methods, like genetic algorithm, similar to annealing, these methods usually involve a very long computation time and do not guarantee an optimal solution. It may take days to get the result. And in this talk, we introduce a new framework. Sparsity or compressive sensing-based methods can be applied here to solve the problem. Formulation is convex, and then you can use existing convex optimization toolbox to solve the problem, and it's just maybe it takes just seconds, then you can get the result. And because it's convex, then you have guaranteed optimal solution for this case. And the whole idea is, okay, first, for given fixed aperture, like 10 lambda, that's a given fixed aperture. So you find the locations of the sensors within this 10 lambda. That's a problem. So for this given fixed aperture is densely sampled with a large number of potential sensors. For example, you can sample it with 1,000 points, right, within this 10 lambda. So you can put each point, you put the sensor there. So you can put 1,000 sensors within this 10 lambda. And for the narrow band case, so each sensor will be followed by a single beamformer coefficient. Then you have 1,000 beamformer coefficient, right? So overall, this 1,000 sensors and 1,000 beamformer coefficients, they form a beamformer with an extremely large number of potential sensors. Then for a given desired beam response, so you know the desired response we want to achieve, and through optimization, we find the minimum number of non-zero valued weight coefficients to generate a response as close to the desired one as possible. So basically, do the optimization under the condition that the design beamformer response will be very close to the desired one. Under this constraint, you find the minimum number of non-zero valued coefficients among these 1,000 coefficients, right? You have 1,000 coefficients, you minimize the number of non-zero valued ones. At the same time, you need to make sure this beamformer will have a response close enough to the desired one. And then after optimization, you may end up with, for example, 10 sensors, 10 coefficients, which are non-zero valued. All the other 990 of them, they are zero valued. And for the sensors corresponding to those 990 coefficients, you can remove them from the design because they have zero value coefficients. That means they are not needed in the beamformer process. So for those sensors with the resultant zero value coefficient, they are inactive in the beamforming process, and therefore can be removed, while those with non-zero value coefficients are kept overall, leading to a final sparse result with optimized sensor locations. So in this case, we have 10 sensors left. That 10 sensors gives you the final design result. Mathematically, so you have this formulation twice. First, you have this vector PR. It's the vector holding the desired reference beam responses at sampled angles, theta L from 0 to this big L minus 1. So in total, L angles, big L angles. Like if for linear array, you have the range from minus 90 degrees to 90 degrees, right? You sample this 180 degrees, this whole range with big L, like 180 of them. So you have theta 0, theta 1, theta 2 until theta 179. So you put the desired response in this vector for different directions, theta. And then for each direction, like theta 0, you have a steering vector. And put all the steering vector, all these steering vectors into a matrix called steering matrix A. And then this W is the coefficients, beamformer coefficients you want to find. And so W Hermitian transpose times this A gives you the design response at those big L directions. And then PR is a desired one. So this PR minus this gives you the difference between the design and the desired responses. And you make sure this error is small enough. You put the limit, this alpha there. So alpha is very small value. And then this is the L0 norm of this beamformer coefficient vector. So L0 norm, basically, you count the number of non-zero valued coefficients. So you minimize this number. And because L0 norm, is not convex, so you use L1 norm as an approximation. So basically minimize this L1 norm subject to the limit on the difference between the designed and desired beam responses. And you can enhance the sparsity of the solution by minimizing a series of weighted L1 minimizations. So instead of minimizing the standard L1 norm, you can modify this L1 norm with this extra factor AM. It's an iterative process. For iteration I, you can calculate this extra weighting factor AM using this. So you use the previous design result WM. So at iteration I minus 1, if the previous coefficient is WM for iteration I minus 1, if this one is large, then the whole thing will be small. If it's small, then the whole thing will be large. You have this extra constant is eta, is very small value to make sure, if this WM is 0, then this whole thing, the inversion of this still meaningful. So otherwise, if it's 0, 1 over 0, it does not work, right, in that case. So we have this eta to ensure stability of this operation. So a small coefficient WM at iteration I minus 1 leads to a large weighting term AM at iteration I, and therefore heavily penalized at the next iteration, while a large coefficient gives a small weighting term more likely to be replicated at the next iteration. So as I said, this is an iterative process, so the problem can be solved using this procedure. So first, set I equals 0, we'll find the initial estimated weight coefficients W using this 13, and then you add 1 to this I and find the weighting term AMI, and then solve the minimization problem in equation 14, right? You find this and repeat these steps from 3 to 5 until the number of non-zero valued coefficients has been constant for a preset number of iterations, like 3 iterations. After 3 iterations, the number of non-zero valued coefficients stays the same, then you can stop the iteration. And then for the robust design, so in practice, the steering vector may not be exactly known due to location errors, mutual coupling, or individual sensor response discrepancies. So you have steering vector error. In that case, you introduce this E, this error vector. So this A tilde is the actual steering vector. A is the assumed steering vector. E is error between these two. And we assume is norm-bounded. So the norm of this error vector, R2 norm, is smaller than or equal to this epsilon. Again, epsilon is a small value. We assume you can derive this epsilon based on your knowledge about these errors. For robust design, we then find the maximum possible change in the resultant beam response due to this error. And then we limit this maximum change to a small value. So you see, that's the real response, that's the assumed response, and the error, the big, this error is given by this, right? And is smaller than or equal to epsilon times this L2 norm of W. So that's the maximum change due to this non-bounded error E. And then you limit this maximum change to a small value gamma. So you add this constraint to this formulation, and then you can find a robust design. So here are some design examples. First is the broadside main beam, and is optimized over overall aperture of 10 lambda, and which is split into 181 potential sensor locations. You see this from 0 to 10 lambda. That's the weight, the magnitude of the weight is W. You see there's 181 of them within this range from 0 to 10 lambda. You see most of them, they are zero valued. Only these peaks, they are non-zero valued. You have 12 of them. So after optimization, you have 12 sensor locations left with non-zero valued beamformer coefficients. And then you consider this 10 lambda. If you do this uniform linear array, lambda over 2 spacing, then you will have 21 sensors. But here we only have 12 sensors. And then here's a comparison of this beamformer response. This blue line is for the design response with these 12 sensors. And this right dashed line is for the URA case, so uniform linear array with 12 sensors. You see the side lobe. So this, because with extra spatial degrees of freedom, right? This side lobe of the sparse array, design sparse array, is much smaller than the uniform linear array. Now for the robust case, again, is for aperture of 10 lambda, and it's split into 300 potential sensor locations. And in this case, you have 14 sensors left, so it's from 0 to 13. And then you look at the beamformer response. You see this is for one particular example, particular design. So the response is good. And here, this one is a mean achieved response. Basically, we introduce the different non-bound steering vector errors, right, of satisfying that non-bounded, that constraint smaller than or equal to epsilon, right? We generate a large number of steering vector errors is E added to the assumed steering vector. Then you calculate the beamformer response. It takes the average. You see this mean achieved response. So still very good, very low side lobe. And for robust design, certainly you don't just look at the mean achieved response. You also want to see the variation, right? The variance. So we have the normalized variance of the beam response is very small. It's very small. So basically, after introducing this error, steering vector error, the change of the beam pattern is also very limited. So it's a robust design result. Now for wideband sparse array design. So although these equations 13, 14, they are effectively in the design of narrowband arrays, they do not guarantee a sparse solution for the wideband case. For wideband sensor array, there are multiple coefficients associated with each sensor location. And 13, 14, these two equations, 13, 14, right? Just look to minimize the number of non-zero valid coefficients without considering which sensor location they are associated with. So what it means is here, okay, given this wideband structure, so if you just minimize the R1 norm of this, all these coefficients, big M times big J, number of coefficients, you minimize the R1 norm, then you may end up with this situation. So for this, for example, consider this sensor 0. So all the G minus 1 coefficients, they may be zero valued, but only one of them is non-zero valued. In that case, although the whole weight vector is sparse, but you cannot remove this sensor because this sensor still have one non-zero value coefficients. So to remove one sensor for the wideband case, right, you need to make sure all the associated coefficients for this particular sensor, they are zero valued. So how do you achieve this in your optimization? The idea is, so you put these coefficients into a vector. So this vector W, you can have one vector here, another vector here, right? This is another vector. You calculate this L2 norm of this vector, of this set of beamformer coefficients, and put all the L2 norms. So you have big M sensors, you have big M L2 norms, right? Put this big M L2 norms into a vector, and then you calculate the L1 norm of this new vector, and you minimize this L1 norm. So in this way, you can have a sparse result. Basically, the whole type data line associated with some sensors will be zero valued after this minimization. And we call this norm L2 norm. So here's the formulation. You see, these are the coefficients associated with sensor M. So you have big J of them. And you calculate the L2 norm, put L2 norm into a vector, you have basically have big M of them. If you add them together, that's the L1 norm of this new vector. And we call it L2 norm. Okay. And so you minimize the L2 norm subject to this what? This beamformer response, this error. So this is desired response, that's the designed response. Make sure the L2 norm of this difference vector is smaller than or equal to a small value alpha. And because it's wideband, so this desired response is not just designed, just not specified on one single frequency. You have big K of them. So frequency 0, omega 0, and omega 1, and omega big K minus 1. As a result, this A is also very big. So you minimize this under this constraint, then you can opt your design result. Certainly, you can also add the norm. This for the robust design, you can add this. So you can add this constraint to achieve a robust design. And you can also have this, or you can also add this is modified with this weighted L1 minimization to enhance the sparsity of the result. For the wideband case, there's another scenario. We call it frequency invariant beamforming. So for the wideband case, for a fixed physical aperture of the ray, then if you change the wavelength of the signal, then the relative aperture of the ray will change. So as a result, if you don't put any constraint in your design, you just design a wideband beamformer, then you will see the beam width of the wideband beamformer will change with respect to frequency. And then in many applications, it's desirable to have a frequency independent response. we call that frequency invariant beamformer, or we can also call it constant beam width beamformer, because the beam width of this beamformer is independent of frequency. It's a constant beam width. Then to achieve that in your design, so you can put this response variation, this parameter there. So what's response variation? Okay, it calculates the variation of the response across different frequencies of the within this range of frequency range of interest. So you see here, you have, this is a response of the beamformer given a W, right? And you see here is omega is an arbitrary point frequency value, and this omega r is a fixed reference frequency. So you calculate, you change omega, you find all the errors between this response at frequency omega and the fixed reference point omega r, and you add all them together. That's a total error, right? If the response is frequency invariant, then this value will be 0, right? So RV will be 0. So to make sure you have a good frequency invariant response, you need to limit this RV to a small value. So limit this RV to a small value, beta squared. Then this RV, because RV can be simplified into this form, matrix form, and then WHQW, so the Q is defined by this. And then you can simplify this constraint into this. It's L Hermitian transpose times W. And this L2 norm smaller than or equal to this beta. And this L is given by this V times U, basically square root of this U. Okay, U is a diagonal matrix containing the eigenvalues of Q, and V is the corresponding eigenvectors. So you can put this constraint there, then the result will be frequency invariant. And one note is, okay, if you need a frequency invariant response over the whole frequency and angle range of interest, then we do not need to define A and PR for each sampled frequency, but just for the reference one. What it means is, okay, you look at this here. If you add a frequency invariant constraint in this formulation, if you add that constraint, then you don't need to consider this big K different frequency points. You can only consider one single frequency in this error, So for example, you only need to consider W omega R or omega 0. You ignore all other frequencies. Because if the response is frequency invariant, then you make sure at one single frequency, the error is small enough, then all the other frequencies will follow due to the constraint imposed by the frequency invariance, this limit. So due to this. So you can simplify this. So you only consider one single frequency if you add this frequency invariant constraint in the formulation. Okay, now here are some design examples. Okay, first is a broadside main beam. So this main beam is 0 degrees. It's broadside. You have saddle region. The normalized frequency range of interest is from 0.5 pi to pi, and the reference frequency is pi. This is the reference frequency for calculating the response variance. And you have M equal to 100 potential active locations spread over an aperture of 10 lambda, and type daily line length is 25. So you see the sensor locations obtained. So we have 11 sensors from sensor 0 to sensor 10. And you can look at the beam response. This is each curve represents one frequency. So you see the result, they are quite frequency invariant, right? The variation of the response over frequency is very small. And now is off broadside main beam design. So you have some main beam direction is 35 degrees, and the normalized frequency range of interest is 0.4 pi to 0.9 pi, and the reference frequency is 0.9 numpy. And again, you have 100 potential locations within this 10 lambda, and target line length is 25. And the result is you have 16 sensors. So 16 sensors. Have more sensors due to this friction, due to this this new requirement, because of broadside. Basically, for wideband beamforming, it's more difficult to achieve frequency environment response if the main beam is at the off broadside direction. So you have more sensors as a result. So 16 sensors in this case, instead of 11 for the broadside case. Here is you have 11 sensors. So that's the design for the wideband case. So conclusions. So a series of sparsity-based design methods has been presented for both narrowband and wideband beamforming, which can be applied to arbitrary array geometries. For the narrowband case, a solution can be obtained by directly maximizing the sparsity of the potential beamforming coefficients, while for the wideband case, group sparsity has to be considered so that the multiple beamforming coefficients associated with a potentially inactive sensor can be minimized simultaneously. And the robustness can be achieved by adding a norm constraint, while a response variation constraint is introduced for frequency environment beamforming for the wideband case. And in our presentation, we didn't consider the size of the antenna. So the physical size of the sensors, so we didn't consider the size of the sensors. However, so if you just do the optimization, consider each antenna as a point, then the result is, possible result is, okay, some sensors, the spacing may be too small. You cannot fit a real antenna there, right? So you have to consider the physical size of the sensors in your design. We have done some work in this direction. You can find them in this reference 7 and 13. And also, we only consider the fixed beamforming case. So the beamforming coefficient is independent of the data. However, we can also apply the idea to the adaptive case for adaptive beamforming. The problem with adaptive beamforming is, okay, for each change of the scenario, then the set of optimum locations obtained will be different. So it's not an easy task. One solution is maybe you consider all beamforming scenarios and you find the average performance with the average set of sensor locations. So basically, the set of sensor locations will give you a response. Will give you an overall good response for all beamforming scenarios. That's for the adaptive beamforming case. And then the design can also be extended to the vector sensor array case, because in our design, we only considered the traditional scalar sensors, right? But the design can be extended to the vector sensor array case. Here are some references closely related to the presentation. It's mainly from my group, okay, the publications. So thank you very much.